Okay, good. We have the recorder fully operational. And so let's talk about exams. First, there are some of you who contacted me by email regarding information on exam dates. I prefer to discuss this information during the lectures because not just for minimizing the number of emails that I get from students, which is not, it's not a negligible purpose because I have some 300 students and, but I prefer that information on exams is openly discussed. I take care of recording any information regarding exams, like how do you make your exam, or what is the weight of the quiz, or etc. I think it is not a good idea if we discuss privately these issues, and also regarding the dates. As I said, I will take care of recording this information, so please make sure before asking private questions that you don't ask something that has been already discussed. Because as I said, I don't want to run the risk that I say only to selected persons some information that may be useful for everybody. Okay, so regarding exam dates, I asked, and unfortunately they were firm in telling me that I'm not allowed to make exams before July 10, which means end of the lecture is June 10. End of the lecture is June 9, and they said, no, sorry, you cannot even June 9 to make an exam. So there is no blockage on the system. In principle, I could do that. On the other hand, this is an experimental course which is taught partially online. I am monitored. I prefer not to take the risk that you have some problems later on. So be patient, and if you have any specific issue, like somebody of you mentioned to me, like I have to apply for a scholarship and the deadline is June 9, I think we have to deal with this issue together with your program coordinator, the degree program coordinator, to try to solve the problem. So if you have any specific issue, as I said, but I don't think there will be an easy solution, but I can try, okay? On the other hand, let's, with the official schedule, let's stick on the dates that we can use. So my proposal for you would be, just 1 second, I open my calendar. For the first exam would be June 12, okay? If you don't have any reservation on that day, okay? And I will publish on Alma Esami the dates, let's say later today or tomorrow, once we agreed on them, okay? Regarding the timing, it depends because some students may have several exams the same day, okay? And regarding the timing, I propose to start at 9, and it is a bit of a problem if I get some requests like I can start only at 11. This is a bit of a problem because the exam starts with a quiz, as you know, and the quiz should be taken all together at the same time. So let's make sure that if you have any clash, you try to resolve it with the other professor. If it becomes something like impossible, just let me know. Let me know possibly by discussing all together, not privately. And then I will try to resolve with the other professor, okay, to see if the other professor can move it or not. Because as I said, it's a bit of a problem. In principle, I could make the quiz at 9 and at 11. But if I make the quiz at 11, I have to stop the orals. And to stop the orals may imply that some of the students have to move to the next day. The next day, I have another exam, so it would mean 2 days later. And this is a bit something that I would like to avoid, okay? I would like to try to conclude the exams on June 12. So even if it's in principle possible to make the quiz in 2 steps, different time windows, I would prefer not, okay? Because as I said, the quiz requires a pause of about 1 hour. Okay, so let's suppose that you come all together at 9. The max capacity that I have for the number of students in 1 day is about 30. Okay, so because the oral will take about 5 minutes per person, so let's suppose 30 persons, and it's 3 hours plus the quiz. So I would say that it's about 30. So if I get more than 30 students, we need to discuss how to manage. Okay, so maybe, as I said, that for some of the students, we make another exam on the 14th. I am free on the 14th. Okay. So this is the situation. If you are less than 30, no problem. We finish during the day. But if you are 30, it will take like until 3, 4 p.m. And then we will see. In terms of sequence in the oral, the sequence doesn't matter with the quiz. You are all together. And in terms, I will try to book a room, a lab, for making the quiz on a PC that is not yours. Not because I don't want you to use your PC. I just want to make sure that there are no problems if I can offer you a PC and then you can use yours. But I will try to book the room. Anyway, this is a detail that we can clarify later. And as I said, the oral will take about 5 minutes. Okay, sorry, the sequence. The sequence in the oral, it makes a difference, because if you are the first to be examined for the oral, you are free at about 10 in the morning. If you are the last, you are free at 3 p.m. Of course, during the time in between, you can move. You can go away and come back. If you have another exam, you can take the other exam. So the timing will be something like between about 10:15, the quiz is finished, and then I start the orals, okay? And if you are the 30th, then of course you come after 3 hours, so you are free to move. And for the sequence in the oral, I propose to use the chronological order of the subscriptions. The subscriptions will open not now, they will open like in May. I propose to open like May 1st, okay? And I propose to follow the sequence of the order of subscriptions, but if you have any specific need the day of the exam, we can discuss it. Okay, so if you have another exam and you are the last one, you want to be the first, we can discuss. Of course, we need the agreement of everybody, so it's not an easy discussion, but just to give you the information of how it works. Okay, any questions so far before I pass to the other dates? Okay. Second date, I cannot make any exam between the 26th of June and the end of June. Let me see, because I am unfortunately or fortunately on vacation in that period. So either we make the second exam like the 22nd after 10 days, or we move like the other students wanted to, we move to July 4th. I have no specific preference. Of course, if we move to, let's suppose that we move to July 4th, and then we make another exam July 18th. And if we make it on June 22nd, I would confirm the date of July 18 or 1 week earlier. So what is my suggestion? I think that if you have an opportunity on June 12 to make another exam after 10 days only, maybe it's not a good option. It's preferable maybe for you. I'm just thinking of you after 3 weeks. Would you agree if we move to July 4th? Second opportunity. Okay, so let me just... Good. And any question? And then what about July 18 for the last one? If you want, I can move along the week. I can postpone it to July 21 or 20. Okay, let's put 18. And then one thing that I probably didn't tell you, you can decline the mark if you try on July 12 and try again on July 3rd. There is no limitation. And then you can decline again July 3rd and try again July 18th, okay? There is no limitation on that. Unless you decline 10 times, maybe that the 10th time I tell you, here there is something wrong, okay? But there is no limitation in principle on trying several times the exam. It happens quite frequently that after the quiz the students say like, no, the mark of the quiz doesn't satisfy me and I try again after 2 weeks. And this may happen. I will give you additional information regarding like if you get 18 in the quiz, what is your chance of getting 30 after the oral or question like that, okay? I will give you additional information when we get close. One thing that I didn't say again, the quiz is different for the students who are not engineers, not studying engineering. The quiz is different. To give you an example, specific questions regarding probability. I know that you don't like probability. So a specific question regarding probability are only for engineering students. I will not ask anything very detailed that goes beyond what is the definition of probability to non-engineering students, okay? Okay, and and if you have additional questions later on, just let me know. This applies also to Erasmus students who are not studying engineering. So maybe that there are students, Erasmus students from master or a degree program on natural sciences. To me, they are non-engineering students, okay? And also the oral will be a bit different, okay? And for now, I am planning to make also the oral to non-engineering students. If I get some problems, like for the first exam, there are like 4 people booked, I may also propose to non-engineering students to make, after the quiz, to accept directly the mark of the quiz. Like if you want to make the oral, you can make the oral. If you are satisfied with 30, which is your mark in the quiz, you can take it, okay? Or if you are satisfied by 25, you can take it. So this may be an option for non-engineering students. Good. I think we are all set with the exams. You will see them on Alma Esami rather soon, but as I said, subscriptions will open, I would say, May 2nd. May 1st is an holiday in Italy, you know, so May 2nd. Okay, is this fine to you if I open like on May 2nd? I think it is a good idea, because if I open now, there are some people rushing for subscribing already now to all the 3 exams, you know, and this is not good because I don't get any information on how many students will take the first one, how many students will take the second one. These are plans that usually you make later on. One thing, if you subscribe to a date and you decide not to take the exam, please, 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 10 times, unsubscribe, because as you will see, I will close the subscriptions about 3 days in advance before the exam date. I need to know how many students in your interest are attending, in your interest, not in my interest. I am booked all the day anyway, but in your interest, you know, if I make a plan for 40 students and there are only 5, you understand, it's not a good management of your day. For my day, it doesn't change much, okay? And these are busy days for you. They are busier for you than for me, because I have, okay, 2 courses to make exam 3, actually, but it's not a big issue for me. To make the exam is easier than, to make the exam as a professor is easier than to make the exam as a student. It's not straightforward also for a professor, keep it in mind. And also keep in mind that some professors, including me, are a bit nervous the day of the exam. So you're not the only one who is nervous. I am also nervous, you know, because, you know, I feel committed to make my best during the exam. So it's not straightforward, but definitely it's easier. You know, when I finished my degree program, when I gave the last exam, I'm not sure if I gave the exam is a good way of saying it in English, but you understood. The last one was a kind of relief for me that you can't understand. Like I was very you know, at my time, there were, I think, the number doesn't change much, but there were 30 exams with 12 credits. So they were really many at the end of the story, because my degree program was 5 years long. In the old system, it was just one, not bachelor plus master only. And after the 30th exam, I was really like relieved, like this is my last exam. I didn't know that it's not the last exam, because then I had to run the context for the position of researcher, and then the position of professor, and then the position of and et cetera, and then the many papers that you have to publish, and any paper is an exam. Anyway, anyway, you understand what I mean. Okay, I think if you don't have any question, I think we can move forward. Questions? And once again, please, I make an effort to reply to all of your emails, but if you have specific questions, like I didn't understand this on this, this is fine. I prefer that even these questions are dealt with during the lectures. But of course, if you have questions that you feel they are real individual, that's fine. But the questions that may be interesting for everybody, please ask them during the lectures. Or look at the videos if you cannot attend. Okay, yeah, one question. Yes, it works this way. There is half an hour duration of the test. After 15 minutes, you are given your mark for the test. And as I said, the mark, you don't need to reply correctly to all the questions to get the maximum mark. Even if you fail a couple of questions, you may get 30 in the quiz. But keep in mind that the oral, even if it's short, it may change the result in both directions. So statistically, it's more or less confirmed, more or less. But it may happen that you get a mark, an overall mark that is 3 scores lower or 3 scores higher. So just keep in mind that the oral may change in both directions. This is an important information, because there are some students who just try, and they say, okay, let me try the quiz. And then the mark is like 25, and then they say, okay, let's try the oral. And these trials, I think, I understand why you try. Also, I tried some of the exams, even if I felt I was not really well prepared. I said, maybe I am lucky. And then, okay, so I understand why you try. But it is important that also you understand the rule of the game. Like, if you want to get 30, my advice is don't try. If you really want to get 30, it's very difficult that you get it just for luckiness. If you are happy with a 25, yeah, maybe. But so, in a way, if after the quiz you see that your mark is 25, you don't get 30. It's very unlikely, unless you are very prepared and the quiz was like an occasional, okay, and by chance failure. So what I tell students, I mean, if you want to get 30 and you got 25 to a quiz, just check that you are really well prepared. You know when you are well prepared and when you are not. You know better than me, of course. So just, I hope I answered your question. Yeah, okay, good. Any other question? Good, perfect. Okay, let me now share the screen. Yeah, let me share the screen just to start. Okay, here we are in our page. I added one link for the exercises today in the morning.
Sorry, the projector.
Yeah, the projector. Good. You know, I wait because sometimes I wait because to prepare the lectures, I need also to read the email information that is not relevant to you. Okay. It's coming, it will come. Yeah, here we are. Okay. So as I said, here we are, and you remember that we started talking about water resources, the motivation why we started talking of water resources is that the impacts of climate change, most of them, as we said, are related to water resources. And also we talked about the distribution of water resources, which corresponds to the distribution of climate. So this is what we discussed the last time. Now I want to go back to risk. You know that I paused the discussion on risk because I understand that is something that may be demanding, so I want to alternate between demanding lectures and lectures that are less demanding in terms of effort that is needed for your attention. Just understand and be patient. Understand that in some cases I need to refer to math, I need to refer to demanding issues, because if you want to talk about adaptation, you need to go technical to some extent. And as I said, regarding especially probability, when we talk about climate change, we need to understand what probability means, because from a technical point of view, climate change is a matter of probabilities. It is something that in order to be quantified, it needs to be quantified deterministically. We don't have certainty about climate change. We have the certainty that something is changing, but when we want to quantify, to give numbers, we don't have a certainty. So this is something that has to be very clear in your minds. Like if we talk about we have lower rainfall into the future, we have a lower amount of water resources into the future, we cannot say 10% less in 2050. We cannot say that. So on the one hand, you understand why some predictions about climate change failed. On the other hand, you also understand why the failure of a prediction doesn't mean that climate change doesn't exist. Climate change is probabilistic. Okay, we don't have, unfortunately, we don't have certainty. Okay, and also when we talk about water resources, it's the same. So I need to talk about probability. I need to make sure that you understand what is the meaning of it. And to understand the meaning, I also want to make practical example. You will see that today we will make some practical examples. Okay, now let's click again on risk-based adaptation design, and let's see where we got so far. We got to the definition of probability, okay, and frequentist definition. Just 1 second, I get to continuous random variables, and we got here more or less, okay, to the definition of probability and computation of probability. And we made some examples, rolling a dice, tossing a coin, and then we turned to the only problem that is conceptually, the only part that is conceptually demanding, which is the definition of probability density. So make sure, I think that I adopted an approach that was very practical to explaining why we need to define a probability density. We need to define it because when we talk about climate, we talk about events that are quantified through real numbers, real variables. So when we talk about rainfall, it's a real number, the amount of rainfall. When we talk about temperature, it's a real number. And therefore, when we talk about events that are quantified through real numbers, if we want to estimate their probability, we have to refer to probability density. And then we computed the density for some of the variables through R. Okay, so on the one hand, we defined probability for integer variables like tossing a coin or rolling a dice. On the other hand, we defined for the same integer variables the cumulative probability, which is the probability of not exceedance. Okay, and then for real variables, we talk about probability density and cumulative probability again. And we said that in a way, the probability density, in order to get the cumulative probability, the probability density does give us the necessary information. And we said that, let me just now change the webcam and go to the blackboard, because I want to emphasize the concept that we said that, 1 second. Okay, now the camera is on the blackboard. We said that the cumulative probability for a real variable, which is the probability of not exceedance, is the integral of the probability density. So what we said in terms of mass, I'm just checking the symbols. 1 second. Yeah, we said that the probability of a real variable, capital X, to be lower or equal than a given value, lowercase x, it's equal to the integral from the lower extreme of the real variable. Let's suppose that it's 0. Now, let's suppose that we talk about rainfall, that capital X is a random variable which defines rainfall. Okay, so the lower value is 0. So from the lower value to x of the probability density in the x. This is what we said. Okay. Probability density multiplied by the x gives us a probability. And if we make the cumulative sum of all the probabilities, we get the probability of not exceedance. It is like for a dice. For a dice, we want to make, 1 second. I got a beep. Yeah, okay. It was a student in the waiting room. So if I want to get the probability that the outcome from the dice is lower or equal than 4, I have to multiply 1/6, which is the probability of getting 1 plus 1/6, which is the probability of getting 2 plus 1/6, probability of getting 3 plus 1/6, probability of getting 4, which is equal to 4 divided by 6, equal to 2/3. It is the same concept. You see, here I computed an integral. An integral is a sum. You don't have to be horrified or concerned by an integral. It's a sum. So basically, here I got the sum of 4 probabilities to get the probability of not exceedance of 4. Okay, and in this case, I get a sum of probability density multiplied by the x, which is probability, and the probability, the same thing. Okay, so we got the definition of cumulative probability. Cumulative probability plus probability density for real variables. Good. The cumulative probability is often called probability of not exceedance. It's also identified with the acronym CDF very often, and the probability density is identified with the acronym PDF. And the CDF is the integral of the PDF. Good. Now, a very, very easy step forward. So far, we estimated probabilities by making experiments, by counting frequencies. Also, the probability density, we estimated it in R. You remember, we made an experiment. And we made an experiment for estimating the probability density. So this is an empirical estimation through experiments. it would be very nice to be able to express these two functions, the CDF and the PDF, the probability and the probability density, analytically. Why it is nice? It is nice because with an analytical treatment, you may estimate probability without making an experiment. And it is also nice because let's suppose that you make an experiment and from a real variable like rainfall, and you get a series of outcomes. How can I make an experiment with rainfall? I observe it every day. And then I get a sequence of outcomes. And these outcomes vary from 0, because when I have no rainfall, it's 0, to a max value that I observed, like 100 millimeters. And then I can estimate the probabilities of these observations, okay, empirically, like we did so far. But if I want to estimate the probability of rainfall to be equal to or less or equal to 200, how can I make this estimation if my observations are up to 100? It's impossible. Empirically, you cannot estimate it. But if I had an analytical function expressing probability, I can extrapolate it also beyond the observations. This is why it's useful to have an analytical function to estimate probabilities. This is the real motivation, the very reason why it's useful. Because if I want to make predictions, I am interested in the extremes. So if I want to know how much rainfall can I expect over Bologna in a very, very dangerous event after climate change, I want to go beyond the observations, because I really want to know what is the probability of getting something really unexpected. What is called a black swan, really unexpected, which after climate change may become expectable. How can I make this estimation if my observations don't show it? If I never got a black swan, how can I estimate the probability of getting a black swan? By the way, there is a literature on black swans. I think I already mentioned it to you. It's interesting. If you go on Google and you digit black swans, there is a literature, because it is a paradigm that is used precisely to identify these events that are really unexpected. So how can I estimate the probability? Only through an analytical function. Only through extrapolation beyond what I observed. This is the challenge of climate change. I have to be able to go beyond what we are used to. We have to get into the unexpected. In terms of probability, I want to know what is the chance. Chance means probability. What is the chance of getting completely flooded in Bologna by the Reno River? Something that we never experienced. What is the chance? I need to elaborate an analytical function to give me the chance, to give me the probability. This is why I think it's a nice example, why I need probabilities and why I need an analytical function. And then the next question from you would be, but what is this analytical function? How it is expressed? And then I can tell you, we don't need to go into details. I will never ask anything at the exam related to specific formulation of probability distributions, of analytical functions describing probabilities. I may ask what are the probability distribution that we discussed. You just have to give the name, not the formulas. I may discuss with you what is the meaning, why I need an analytical formulation of probability distribution, and then you have to provide an answer that is coherent with what I just said. Okay. And but I just want to tell you that there are several formulations provided by the literature. And the fact that we have several, it's a bit of a challenge, because it means that we have several alternatives. And how can I select the best one? Because if you use different probability distribution, you get different predictions. If you use different climate models, you get different predictions. So what is the best one? The best one is the one that fits the data that I observed best. So I try to describe the probabilities that I computed through my experiment, computed empirically, with a mathematical model, and then I see what is the model that performs better. This is the same for climate models. They are used to reproduce what we observed, the climate observed in the past, and then we select the model that best reproduces the past. Okay. In terms of probability distributions, there are two distributions that I want to mention to you. First of all, let me make a premise. In order to give a formula for probability, you may decide to describe the cumulative probability or the probability density. It is all in all equivalent, because one is the integral of the other. So it doesn't really matter if you describe the probability density or the cumulative probability. You can give an analytical formulation for the cumulative probability, and then you compute the derivative, and you get the density. Or you can define the density, you compute the integral, and get the cumulative. So in some cases, the literature provides a formulation for the density and the formulation or the formulation for the cumulative. Why? You may wonder why the literature sometimes gives to me the density, sometimes it gives to me both, sometimes only the cumulative. The reason is that an analytical function cannot be always integrated analytically. So there might be an analytical expression for the density without a corresponding analytical expression for the integral. And therefore the literature only gives the density. And then you may say, but how can I compute then the integral numerically? You know that you can compute the integrals numerically or analytically. And if it cannot be computed analytically, you cannot write down an analytical formulation, but you can compute it numerically. No problem at all. Because the integral is a sum. Nothing more than a sum. It is the easiest computation that we learn to make at the primary school. The integral is a sum. Numerical is a sum. Okay, so let's look at the screen now to give you a couple of, just one, I would say, example of probability distribution, which is the normal distribution. I think almost all of you had some background in probability, maybe at the high school or during your bachelor. And if you had some background, you had also a mention on the normal distribution or Gaussian distribution. What you see on the screen now, it's first, just 1 second, I'm not sure I can open this. Let me see. No, it is, I don't think it can be zoomed out. Just 1 second. Yeah, it can be zoomed out. You see on the screen now the analytical formulation of the probability density of the normal distribution. The normal distribution is just a distribution. It is very easy in terms of understanding what it means. It is, the analytical formulation is not so easy. You don't have to remember it, absolutely. You just have to get the concept, which I am explaining now. First of all, it's not analytically, how to say, the integral cannot be analytically computed. So you only get the analytical formulation for the density, which is probability density, lowercase p, the same symbol that you can see on the blackboard, of given value x of a random variable, okay, which is conditioned here. The vertical bar means conditioned. It means that the probability is conditioned to what? It is conditioned to two parameters. What are parameters in an analytical formulation? In an analytical function, what are the parameters? Let me give you an example. A very easy example of a function with two parameters, which is the analytical formulation of a straight line. A straight line, you can write it in this way. Y is equal to A times X plus B. This is a straight line. If you plot it into a graph, it is a straight line where B is the intercept, this is B, and the slope is A. Okay. It's a straight line. It remains a straight line even if you change B and A. It remains a straight line. But if you change B and A, the position of the straight line and the slope changes. So the parameters in analytical formulation are defined as coefficient that don't alter the general shape of the analytical function, but change their specific shape. So the general shape is not changed, it's still a straight line, but the specific shape, location, and slope changed. So these are the parameters. So in a way, the parameters allow you to adapt the analytical function to your needs, to describe the process that you need to describe. So I can use this straight line to describe, for instance, the increasing temperature along time in Bologna. But in order to describe this process, I need to adapt B and A. And if the increase is very steep, I need a higher A. If the increase is negligible, A is close to 0. So I am adapting the general shape of the straight line to describe the process that I need to describe. So, as for the straight line, the expression of the normal distribution has two parameters. They don't change the general shape, but I can adapt the two parameters to describe the data that I need to describe. So what is the general shape of the normal distribution? First of all, the normal distribution is also called the Gaussian distribution, in honor of the famous statistician Gauss. So they are synonyms. You can hear people talking about the Gaussian distribution. You can hear people talking of the normal distribution. They are the same. Okay, the general shape is that in this graph you can see several general shapes of the Gaussian distribution for different values of the two parameters. They are called here mu and sigma. So, first of all, the general shape is a bell. It's a symmetric bell. Symmetric. You see that the bell is symmetric around the top of the bell. It's mirrored on the two sides. So it's a symmetric distribution. The fact that it's symmetric is entertaining because it means simplicity. You understand, beyond the analytical formulation, if you see something symmetric, from an engineering point of view, we are always happy. Like think of a building, when it's symmetric, a structure in general, a bridge. When it's symmetric, we are happier as engineers because we understand that this is a feature that makes the structure more easily described. Okay, so the normal distribution, the fact that it's symmetric, is not just something that occurred by chance. Of course, we want something easy. So it's symmetric, and the two parameters, let's talk about the two parameters. Mi corresponds to the highest density of probability. So you see the blue line has a mi of 0, and also the red line and the yellow line. And you see that they are the top of over 0, the top of the density over 0. So mi, again, is the location of the highest density. The green probability distribution has a mi of -2. You see, it's here. The top is at -2. So mi is a location parameter. We can shift the bell along the values of what we want to describe. And this is very useful because, of course, if I describe rainfall, I want the highest probability located exactly where I observed most of the density. So if I have much of the data that are equivalent to 0 in rainfall, I want the max of the probability at 0. So it is a good opportunity, the fact that I can move the bell along the values. What is described? What feature is described by sigma? It's you see, it's the width of the bell. The lowest sigma here is for the blue distribution, and you see that the blue distribution, the bell, is not very large. The other distribution for increasing sigma, it is increased the width of the bell. And an interesting question for you: why, if the bell becomes larger, the max density becomes lower? So if you can reply to this question, I don't want the reply to you, but if you can reply by yourself in your mind to this question, it means that you understood so far. It's a very simple question, like why, if the bell is larger, the density is lower? You see that the amount of the top density is indeed related to sigma. So why? Bell larger, I give you some time to think of it. It is, the reason is simply related in the formula that I said so far. So B of x lower of f1, then, sorry, big X lower of f1, then a given value x, z of the integral. In this case, the normal distribution doesn't have a lower limit. So from minus infinity to x of bx in the x. And we said this is probability of not exceedance. Let me call it PLE. Now, if I here instead of x, I write, let me delete and replace infinity. And then the integral becomes from minus infinity to infinity. What is the result here? What is the probability of not exceedance of infinity? Which one? Because it's the cumulative probability. Cumulative probability of not exceedance of infinity is 1. Okay, so if the sum, if the integral of the bells must always be 1, if I enlarge the base of the bell, I have to decrease the top, because the area below the bell must be always 1. If you didn't understand by yourself, don't be concerned. I just wanted to, this is not an easy question at the beginning. Okay, so this is the normal distribution. There is one thing that I just said, the fact that the domain of the normal distribution is from minus infinity to infinity. It's unbounded. You see here, -5. So this means that if I want to use the normal distribution for rainfall data, it's not a good thing, because rainfall data are bounded by 0. The lower limit is 0. So if they are bounded, it means that if I want to sketch on the blackboard a possible probability distribution for rainfall data, the lower value must be 0. And then I can go up to infinity. This is fine. but I cannot go below 0 rainfall. It's a non-negative variable. So what could be a possible distribution? A possible distribution must give some probability to 0, some density. So this is my PDX. Some density to 0, because I have some zeros. And then I may have a peak of density to some value, and then a tail that for rainfall tending to infinity tends to 0, asymptotically maybe. This is a distribution that is then non-symmetric. Cannot be symmetric if there is a lower bound. Cannot be symmetric. It could also be another possible distribution. Could be also this one. If I have several zeros, it could also be this one. Anyway, it's not symmetric. And this is the PDF. It's the density. And if I want the cumulative probability, I just have to compute the integral here. So this means that the normal distribution for describing rainfall is not a good thing. On the other hand, the normal distribution could be used for describing random variables that are only positive. This is possible. I mean, if I have a top density that is very high, I can describe with the normal distribution variables that are only positive. It's not bounded in principle, but in practice it could provide a reasonable approximation for only positive values. Okay, and in fact, why is the normal distribution so interesting? If it cannot be used for describing some type of variables, why I am mentioning to you the normal distribution? It is interesting, the normal distribution, because there is a theorem, which we don't describe in detail, which says that whatever is a random variable that you consider, rainfall, earthquake intensity, temperature, whatever is it, if you take the average over a time window and you increase the length of the time window, so rainfall, total rainfall during a year, total rainfall for 10 years, total rainfall for 100 years. So you take the cumulative sum, which is the same thing than the average. So if you take the average or the cumulative sum, it's the same thing. The average is equivalent to the cumulative sum. And you compute this statistic average, for instance, over time window of increasing length, then you converge to a normal distribution. This is interesting. This is also nice because it means that in the game of chance, there is some regularity, which is understandable, because if you think of observing rainfall every day, it is difficult to make a prediction. But if one asks you, what is the annual rainfall in Bologna? I told you what is annual rainfall in Bologna, I think. It's about 650 millimeters. This is the average. It is much of an easier prediction. If I am asked to say, what is the amount of daily rainfall this year on July 12th? It's impossible. Now you cannot make such a prediction. There is no idea. No idea. But if I am asked, what is the rainfall in Bologna that you are expecting for 2024? I would say between 600 and 700 with high confidence. So when you aggregate a variable over time, it becomes easier to anticipate it, to describe the game of chance. And this is why you converge to the normal distribution. But on the other hand, the concept is very interesting. It means that by referring to the appropriate time scale, it's easier to make a prediction. And this is why also climate predictions, they don't tell you in 2050 there will be a rainfall of a given number. They give you a prediction in terms of average. They tell you in 2050 you will have an average annual rainfall of 10% lower. They don't say you will have a monthly rainfall which is 10% lower. They aggregate over the long time. Good. So, normal distribution then. I don't think it is a good idea to consider additional distribution. I just wanted to mention to you that there is an easy extension of the normal distribution that makes it applicable also to variables that are bounded by 0. The easy extension is the log normal distribution. You take just the logarithm of your observations and you describe them with a normal distribution. So if before applying the normal distribution, you take the logarithm of your observations, then you can apply the normal distribution. This is an easy extension, the log normal distribution. Just keep it in mind, and there is no mention of it on my web pages. I just wanted to mention it because we often take the logarithm when we fail to describe a random variable with the normal distribution. The first thing that we try is to take the logarithm and then try again with the normal distribution. And in this way, we apply the log normal distribution. Okay, now I want to give you a practical example now at this stage in order to show to you that what we discuss is very simple, actually. And in order to discuss with you what is, to show to you what is the information, the very relevant information about climate that a probability distribution delivers. So in a way, when you deal with something related to climate in a quantitative way, the first thing that you should do is to identify what is the random variable of interest, like temperature, like earthquake intensity, like number of forest fires, this is an integer, and look at the probability distribution. This is the first thing that you should do. Look at a plot of the variable and the probability distribution. So let's suppose that you are concerned by increasing temperature in Bologna. You should get the observations. You have to get familiar with the process. You cannot talk of something in a quantitative way if you don't see the numbers. And see the numbers means that you get the data, you plot them, and you look at the probability distribution. This is what I want to convey to you. And this is why I took 4 of your studying hours to get back to the concept of probability distribution. So let's look at our web page of the course, and let me go back with the camera to the overall view. Okay, let's go back to the page of the course. Let's go down. There is a new exercise, computation of the probability density function for the Po River at Ponte Lago Scuro. So let's click on it. I think there is a PDF. Let's read there is a PDF, and there is in the zip file there is a series of data. Let's look at the PDF first. Okay, computation of the probability distribution for the Po River at Ponte Lago Scuro. So, just one second. at the river cross section of the Po River at Ponte Lagoscuro. When you talk of a river, you have to say where. So Ponte Lagoscuro is a location along the Po River. It is conventionally identified as the closure of the Po River basin. So it's the last gauging station, and they gauge there the river flow, okay? The amount of water that passes along the Po River, this is the river flow. And so we have daily observations of river flow from, in this case, January 1st, 1920, up to December 31st, 2009. Daily river flow means that every day somebody measured the volume of water per unit time that is passing by. It's a very long time series. It's about 32,000 numbers because it's 90 years times 365 days. So it's a huge number, a huge amount of data. This is a good record, okay? And the data are expressed in cubic meters per second. As I said, it's volume of water per unit time. And they are reported in a text file with the data observed on February 29th of leap years that have been removed. So we are kindly requested to estimate the probability density distribution with R for the overall observation period and two different time periods obtained by splitting the observation period in two windows of equal length. And then we have to estimate the cumulative probability distribution and plot this distribution in graphs. So let's go into R. First of all, I am committed to put in the website also an example of R file, okay? Let's go into R now, and let's suppose that we already, sorry, there is the R window. And let me increase the font. Let's suppose that we have already uploaded the time series, but in a way, if you put this file, text file, Po Ponte Lagoscuro, text file, which is included in the zip file that you downloaded from my website. If you put this text file into the documents directory, documenti here, documents of your Windows PC, and you start R, you can upload it with a very simple instruction. You have to define a name for the vector, like Po River is equal to scan, and then you have to open commas and write the name of the file. I just completed the name by pressing the tab. And if you push return, you see that it reads 32,850 items. These are daily observations. Good. As I said, we are asked here to discuss about climate change on river flows. So what we just did is to get the numbers. Now, I said, second thing is to plot the numbers. Plot Po River. And let's put a line as a type, because if you put points, let's put points first, see what happens. See what happens. It's hardly legible with points. Better lines, okay? So let me go back to the R console. With the arrow up, I recalled the previous instruction, and now I'm changing the type of the graph to line. Good. Here is the plot. 1 second. So look at the plot. You get a lot of information here. Very easy information. First, you see that the max is around 10,000, and the unit is, as we just learned, cubic meters per second. Okay, And you know that there has been some floods over the Po River in the considered period. The last one was in 2000, which is the big, the last peak that you see on the right. And so you get already an information of the max flow that you can expect from the Po River, which is, as you see on the graph, about 10,000 cubic meters per second. This is daily average. It's not the peak. It's not the highest peak, it's daily average, okay? Also, if you look at the graph here, you don't see clear signs of change from 1920 to 2009. I said clear signs because maybe that if we focus only on the summer flow, we see a change. Here we are focusing on the daily flows. And it's clear that there is no a clear change here. It looks, if we look at a trend, we don't see a trend. And also, you know, the general feature of the time series didn't change much. But this is just an overview, an overall, you know, okay. But then we need the probability distribution. We know that in R it is quite simple to compute it. We did it. So let me just do it. Plot density. We have a function in R that gives the density function. So let's use it. Density Po River. Again, let's do type equal line. This is the probability distribution of the Po River daily flows. Nice. Let me put also the points here. Type both. Good. There is a lot of information here. A lot of information. What you can see here is the max. It's much easier to see the max. It's around 10,000, which corresponds to what we could see on the previous plot. And you can see what is the most probable value. It's around, I would say, here is 1,000. It's a little bit more than 1,000. This is the most probable value. I mean, it's good information because what is the most probable value? It's close to the average. It's close to the average. We will compute the average now, but the probability distribution tells you something. Of course, what I am expecting is that given that the distribution is not symmetric, the average is influenced by the long tail. So the average will be a little bit more than the max density of probability. Because the max density is the value that I observed more. But this value that I observed more is, in terms of average, is shifted on the right by the high observations. So I am expecting that the average is a little bit more than 1,000 plus something. Okay. The max density, I would say, it's around maybe 1,200. For the average, I expect a bit more. And another important information is given by the width of this probability distribution. There is not really much variability here. You see that most of the values are below 4,000. Most of them. What remains after 4,000 is just a long tail with very low density. I use the term tail, right tail, in a proper manner. When you listen about the tail of the probability distribution, the tails or the right tail, this is what they mean. A right tail, which is very long, is a bit of a concern, because it means that with very low probability, I may have huge floods. So it's a lot of information. And, but you lost one essential information here with respect to the previous plot. This gives you more information, but you lost something important. Let me recall the previous one. You see, this is less informative, but it gives to you an important information which is not delivered by what is the essential information? Let me go back again to the plot. Okay. What is the essential information here? It's just what I discussed, change. Here you see information on the chronological order of the observations. When you pass to this plot here, the chronological order is not there. Okay, and I talked about the average. Let's see what is the average. It is easy with R to compute the average. But before the average, let me compute the median. What is the median? The median is the value with the highest density. Let's say it's not really that. I'm sorry, this is a mistake. It's the mode, the value with the highest density. I'm not sure if the mode in R is computed with the function mode. Let's see. Not really. So given that I don't remember how to compute the mode, let me check with the help. And I prefer to go directly on the web. So project. R mean, median, and mode. Just 1 second. Mean, let me see. Median, let me check for the mode. Oh. There is no direct function to compute it. You know, R does not have a standard inbuilt function to compute the mode. Let's forget about it for now. Let's just look at the average. Okay, mean 1500. And if I look at the mode, it's around 1200, I would say. Okay. Now, let's go back to this plot here. And let me ask you one question now, or let's ask all of us one question. This is an empirical probability distribution, empirical, okay? And empirical means that I computed it through an experiment, as I said, by just counting the number of times the numbers fall within a given range. Now, the question for all of us is we have to find a candidate analytical now representation, because we want to extrapolate. For instance, is the normal distribution a good candidate to describe this empirical probability distribution? The answer is no, because this one is not symmetric. Now, is the log normal distribution a good candidate? Well, we don't know. Let's try to make here, to plot here the density of the log normal distribution. And it's not so easy to make it in R. What I would prefer is to compute it empirically. So let's try to compute, let's suppose that the data are not normally distributed, and then I compute the empirical log normal distribution. So I propose that let's forget about this procedure for now. I'm showing to you what I'm doing over R. Maybe that some of you understand what I'm doing, but I would prefer not to make the discussion too complicated at this stage. So let me just with a very simple calculation in R to plot here the log normal distribution and make the comparison. Okay, so what I need to do is let me just recall it. First of all, I have to compute the empirical frequency distribution of the data, and this is what I need to do. And then I need to estimate the log normal distribution of these probabilities. So with the first instruction, I estimated the empirical distribution, the empirical probabilities of the Po River daily flows, and now I'm computing the inverse of the log normal distribution of this probability to get log normal data. I think this should be fine. And now I can plot the two graphs. Let me plot first the density of the log normal distribution. So let me see here. And here I would prefer to make a line to make it red. And give it a double width. Let me see how it looks. Okay, this is a log normal distribution estimated for the Po River data. Now let me plot the density of the Po River data. I'm not sure if it works. Let's see. Yeah, it works. Okay. So you see that the fit, the description is not really perfect, because let me just extend a little bit the probabilities. Let me extend a little bit the vertical axis. Whether this works, let's see. No. How it works. Now it is legible. So you see, on the dots are the result of the empirical computation for the Po River flows, and the red is the description of these probabilities with the log normal distribution. I mean, it's not really very good, and this, in a way, was expected by me. It means that I have to do for another representation. The log normal distribution, what it does, it overestimates the variability. You see that the tail is pushed to 14, almost 14 thousandths. And there is, of course, given that the variability, the pitch of the bell is overestimated, there is an underestimation of the peak of probability. So this wouldn't be really a satisfactory fit. But through this red line, you see that I can estimate probabilities for, I can extrapolate. I can go beyond the probabilities empirically estimated with the data. I can extrapolate. And the red one is an analytical representation. I computed it in R numerically. And once again, forget what I did in R. Okay? We don't need to understand it now. And even later, we don't need to understand it. What we need to understand is the concept of probability density. So the concept of cumulative probability and probability density. We need to understand how probability density is introduced. We need to get well established that the cumulative probability is the integral of the probability density. And we have to get that both of them can be described with an analytical relationship. The literature provides different alternatives, and it is important that we select the alternative that gives the best fit of the data. The fit that you see here is reasonable, but not very good. Okay, now, before the break, I just want to move a step forward in this exercise, and I want to estimate the empirical distribution, the red point, the black points, for the two time windows. from 1920 to 19 more or less 65, and from 1965 to 2009. Why? Because I want to see if there has been a change in time. So I want, in a way, get the chronological information that is not delivered by the overall probability distribution. Okay, let's make it. It is very simple. First of all, let me plot once again the black points alone. I clear the screen. Good. This is the overall graph. Okay. Now I just have to make the plot of the density of the Po River. Remember, the total length is 32,850. So let me compute the density between 1 and 16,425. Gave the indexes to the vector for the first half. Let's see. Density. Good. Now let's this plot lines. Density Po River from 16,426 up to the end. I can omit the second index, and let's put only a line, but let's make it red. And let's make a twice width. Sorry. Maybe that I have to make the last index. Yeah, okay. I needed to give also the second index. It was not true that I could omit it. Okay, this is the distribution. Actually, the changes are not so relevant. And let's say that in order to see the whole of both plots, I have to extend again the y-axis, the vertical axis. So let me extend it, okay? I don't remember I need to extend to 9e minus. There are no big changes, but actually what I can see is that in terms of extremes, the second half of the series is a bit lower. You see that the red line stops here. So the first probability distribution was covering a wider range. So indeed, I don't see very big changes here. Also, if I look at the droughts, you see that the black points have a little bit higher probability density, which means that I had a greater chance of finding these low values. So it means that also in terms of droughts, given that I had a higher chance of finding the low values, the risk of drought was more evident in the first half of the period. But this is something that matches with what we know. And what we know is that between 1940 and 1950, the Po River, there was a huge drought that lasted for about 10 years, which didn't occur in the remaining years up to 2009. And then after 2009, we got some more droughts, and the 2022 drought was the worst in terms of duration of only 1 year, in terms of seasonal droughts. It's still lasting, but we still don't know how long it will be. But I mean, what I wanted to say is that probably the fact that we had this drought period between 1940 and 1950 conditioned this also overestimation in the first period of the drought risk. Do you have any question? I hope you understood why we need to look at this graph when we talk about climate change. For every variable that we may consider, if we want to talk about a change after global warming, in whatever environmental variable, we need to look at the probability distribution, plot and probability distribution. And this is why I really needed that you became able to understand what a probability distribution is, what probability density is. Otherwise, it's impossible to talk about these issues. Good, let's take a coffee.
sostanziale. Sono chiuse. Sono le chiavi.
Okay, I am a bit late. I apologize. Okay, let's conclude this discussion. Oh, let me just conclude it by showing how to compute the cumulative density distribution, which is very easy. And let me make it for the overall time period. The density for the overall time period, I think, let me compute the density separately. I give a variable to density distribution, which is like, this is PR1 is just the name of a variable. And if I assign the density to a variable, what I get is a list with X and Y. And you see here, the result of the computation of the density distribution into R is a list, which means a set of different variables. The first two variables are X and Y. X and Y are the coordinates of the density. If I make a plot of PR1X, PR1Y, I get precisely the density distribution. Okay, so what I just have to do now is to make a plot of, I keep the same X, Y, the Y in this plot here, I substitute the Y, the vertical axis, with the cumulative sum of it. Result.
This is over micro tables,
Okay, be careful, remote students, keep the micro closed and open it only if you need to talk. Okay, good. This is the cumulative distribution function. Okay, just as a result of the sum of the density, the integral is a sum. Okay, actually, I should. There is something more that I have to add. In order to compute the cumulative density, I have to take the sum of the density multiplied by the delta x. You see the integral. It's the cumulative sum multiplied by the delta x, which is not reported here. This is why the cumulative density doesn't sum up to 1. Just forget about it, okay? The result should sum up to 1. Here, it doesn't sum up to 1 just because I forgot to multiply by the x. Let's forget about it for now. I'm not correcting this graph. The shape remains the same. You just have to rescale the axis, the vertical axis. Do you have any questions? Okay, let's close this discussion on probability. We are done here. And I just want to now go back to risk estimation. You remember that we basically talked about probability because we wanted to, wait a moment for the opening of the web page, we wanted to get the factor of the risk equation, sorry, just 1 second. I want to make one thing. I want to log out from here because otherwise, 1 second, give me a second, log out, perfect. Okay, and then I click again on risk estimation. Good. So I wanted to get the factors of this multiplication, probability, vulnerability, and exposure. So we discussed, as you may remember, we discussed already what are vulnerability and exposure, and then we started the discussion on probability, which is also called hazard in the context of risk estimation. The probability, which may be cumulative probability if we are talking about a real variable, or maybe a probability, a generic probability if we talk about an event, a risk that may be quantified through integer variables. The probability is what we discussed so far. Okay. Now, let's discuss some more this equation here. So let's try to summarize our discussion on risk. And what I want to say now is that for a considered event, like a flood, okay, we now are able to estimate the probability. We can estimate the vulnerability. We said we can estimate it. Vulnerability means the degree of protection, and we can estimate the exposure. Remember that probability doesn't have a unit. It's adimensional, it's dimensionless. Vulnerability, we said that is variable in the range of 0, 1. It's an estimate of your degree of protection. It doesn't have a unit. Exposure has usually a monetary unit. So the result, the risk, is monetary. Now, we learned that extreme events, very extreme ones, so the very extreme flood, we learned that has a small probability. If you think of the density of the Po River, which we just saw, the floods, the higher value are in the tail with very low probability density. So this event has a low probability. On the other hand, this event, when they occur, they have they generate a high exposure. The flooded area is larger. So what is the moral of the story? Exposure is depending on the probability of the event. It's not a constant. It's not a constant. The same for vulnerability. Vulnerability is the degree of protection by, for instance, a levee. But the levee has an upper limit in terms of protection. If the flood exceeds the height of the levee, you get flooded, even if there is the levee. So also vulnerability depends on probability. This is easy to be understood. And I would say, fortunately, they depend on probability. Why? Because let's suppose that vulnerability and exposure are constant. For small floods, we have the same vulnerability and exposure than for big floods. This would mean that I wouldn't be concerned by big floods. I would be more concerned by low floods, because the big floods, they have a very small probability, and therefore the risk, associated risk, would be very low. So, and this would be a mistake. It would be a mistake because, you know, the small flood doesn't actually is a matter of concern. The matter of concern is the huge one. Why? Because exposure is increasing. So what is the moral of this reasoning? The moral is that I have to take into account this fact, which is a bit counterintuitive, which says that maybe that I don't have a good reason to be concerned by the very huge flood, unless it really creates a big exposure. So I have to study in detail the dependence between, in order to estimate the risk, in order to estimate the priority to adapt to an event, I have to understand not only probability, but also the dependence of vulnerability and exposure on probability. And I think that we can adopt a graphical approach to better clarify what I mean. So, what is the purpose of this graphical approach? To estimate for each given event probability, vulnerability, and exposure all together with an holistic approach, not separately. So, big flood, I first estimate the probability, and then depending on the probability, vulnerability and exposure, depending on the probability of the flood, which depends on the flood itself, of course, then vulnerability and exposure. What is the purpose? The purpose is to identify what is the event that originates the greater risk. Okay, good. Now, let's, as I said, take a graphical approach. But before I show you this graphical approach, let me introduce a concept which is, I think, helps also to understand probability, and a concept that is used in technical terms. In technical terms, often we engineer, when we talk about the hazard of an event, we may talk of probability, but this is more scientific. In technical terms, we prefer to use the term return period, which is more understandable than probability. Return period, what is return period? Let me write on the blackboard. The return period of a given event, so return period of a given event, period of Okay, so the return period of a given event is the average time lapse. I write it because it is something that I really want you to learn and to have clear. Is the average time between two events with equal or greater intensity with equal or greater. Let me write it in this way, which is short and for yours to assign the intensity. So I may say, what is the return period of an earthquake, which is which corresponds to the 7 Richter scale for Bologna. So the assigned intensity is the 7 Richter scale. And I may say it's 30, no, not 30, Richter scale 7 in Bologna, it's 1,000 years. What does this mean? That I am expecting a time lapse of, on average, 1,000 years between two earthquakes in Bologna with intensity greater or equal to the 7 Richter scale. Okay, if you read the definition, in this case our event is an earthquake with an assigned intensity of grade 7 Richter scale. I have estimated the average time between two earthquakes with equal or greater 7 Richter scale. This is technically quite useful because it tells you information about the frequency of a threat induced by climate change. The earthquake is not necessarily induced by climate change, so we can talk about temperature. So what is the average time lapse between two max daily temperature in Bologna passing 40 degrees Celsius? So every year I estimate the max temperature in Bologna, and let's say 45 degrees, because 40 is something that is quite frequent. 45 degrees is quite rare. So how many years are passing between observing max daily temperature in Bologna of more than 45 degrees? I would say 8 years, which means that, 45 degrees I observe in Bologna on average once every 8 years. Okay. Of course, it is related to frequency, no? The return period is related to frequency. And frequency is related to probability. So you understand that the return period is a synonym of probability of not exceedance, or in this case, it's probability of exceedance, which is the same thing. Okay. And so, for instance, let's suppose that we refer to annual max temperature, annual max. So I have one measurement every year in Bologna, annual max. And let's get, for instance, a value in Bologna that is exceeded on average only once in 100 years. What is the probability of this? Probability would be something like 1 over 100. Okay? So it is exceeded with a probability of 0.01. And it is not exceeded with a probability of, so not exceedance is not exceedance is 0.99. Okay, so the temperature, the max temperature in 100 years is equaled or exceeded only one time over 100 experiments, 100 trials. So it has a probability of exceedance of 0.01, probability of equaling or exceedance of 0.01. So not exceedance is 0.99. So you see the return period is related to probability. Okay. And increasing return period means increasing probability of not exceedance, decreasing probability of exceedance. Okay, so let's look at the graph that I wanted to show you. Let's forget about probability estimation, we already discussed it. Okay, this graph that I wanted to show you. If you look on the screen, so here you have the intensity of the event. It can be also quantified here in terms of return period or probability. Okay, you can associate to the intensity of the event a return period or a probability. Okay. Now let's see what happens to the intensity of the event to the exposure and vulnerability. Let's look at the blue line, exposure. I am expecting for low intensity, no exposure, no damage. If the flood is very small, if the earthquake is an earthquake with very low intensity, no damage. And then there is, for increasing intensity of the event and increasing damage, and then we can think of an upper limit to the exposure. When everything is destroyed, even if I get an event with a higher intensity, I get an asymptotic tendency. When everything is destroyed, I have a maximum exposure. Estimating this curve is not easy. You need a very technical analysis. For instance, if I get an earthquake of grade 1, no damage, 0. But then for increasing intensity of the earthquake, I get some buildings that collapse, increasing exposure. I'm only talking about economic damage. Let's forget the deaths of people, because I don't think it is ethically encouraging, ethically correct to talk about. I prefer to make the assumption that people are not at risk. Okay, I think that if people are at risk, I have to make another graph, another evaluation. We already discussed this. Okay, so let's focus only on the building that at a certain intensity of the earthquake start to collapse. And then at a given intensity of the earthquake, everything is destroyed. Okay, this evaluation is not easy. It is very local. It depends on the case. Okay, very local usually. This is a kind of shape of this curve that I think it is reasonable. Now let's talk about vulnerability. We have a similar situation. Vulnerability ranges between 0 and 1, as I said. And for given intensity of the event, vulnerability is 0. So if every building is protected against the earthquake up to a certain intensity, so let's suppose that any building is earthquake-proofed up to the intensity of, say, 4 Richter scale. So we are sure that no building collapses because they are protected. Okay? Exposure was estimated by assuming that there was no protection. In this case, let's suppose that buildings up to the scale of 4 are protected. And I can give you a more meaningful example to understand that the exposure may start to increase with at a different intensity with respect to vulnerability. Think of floods. I may be protected by a flood, by a levee. The levee is overtopped here. But what happens if the levee collapses before being overtopped? Then I have an exposure. So you understand that I have to consider separately the exposure with respect to vulnerability. I cannot say just, no, I have the levee and therefore up to here, I can assume that nobody's flooded. And if the levee breaks, if the levee collapses, what happens? So I have to first make the evaluation of exposure by assuming that the levee is not there, the protection, the adaptation is not there, and then I consider the effect of the levee, adaptation, vulnerability. So it's 0 up to certain intensity, and then there is an increase of vulnerability. And at a certain point, you may have that vulnerability is 1. The max is reached. When the levee is overtopped, vulnerability is 1. Now, you can also show here the product, the result of the product between probability, vulnerability, and exposure. Keep in mind that here, as I travel towards the right of the axis, probability is decreasing because we learned that. I am traveling along the direction of decreasing probabilities. So risk is 0 up to here. Why? Because vulnerability is 0. Vulnerability is 0, risk is 0. Then, when I have the start of the race of vulnerability, I compute the product between vulnerability, exposure, and probability, which is decreasing. Very often, you understand, you end up with a top in the curve of risk. And then, given that probability decreases, keeps decreasing, while vulnerability and exposure don't keep increasing because they are getting close to their max, then you have the risk that is decreasing. So the risk is not necessarily given by the highest possible event. If the highest possible event has a low probability, then you get a decline of the risk, which means that this is the intensity I am most concerned of. Okay? Good. This is the reasoning that closes our discussion on risk estimation. We closed the circle. We talked about estimation of vulnerability and exposure, and then we gave this additional food for thought about vulnerability and exposure. We talked about probability estimation, and then we closed the circle by saying now we have the means to estimate the max, the event that gives the max risk. So a good choice could be I adapt against this event. I give up adapting to the events which gives to me a low risk. Okay. Now let me, I said, we concluded this reasoning, but let me tell you, let me anticipate that we will discuss later on about limitation of this reasoning, which is being pointed out by the literature very recently, and which is still discussed today by the literature. So the literature says, okay, according to this reasoning, you give up, as I said, getting protected against events with the low, very low probability. Why do we give up? Because we may not have the resources. Because adapting to events, ensuring that we are adapting means that you take the threat card and you bring it down. Adapting. But of course, the more you bring it down, and the more costly the adaptation procedure is. And you may have not the means for getting adapted to an event that is very rare. Okay? And we cannot get a full protection anyway. So when we talk about natural hazards and climate change induced natural hazards, a full protection, it doesn't exist. These variables don't have an upper limit. So you cannot say what is the upper limit of an earthquake intensity. You cannot say what is the upper limit for a flood. It's by definition, they don't have an upper limit. You may get a flood that occurs once in a million of years. And it's impossible to get protected against that. So for sure, we have to give up to some risks, to getting protected with respect to some risks, for sure. So it is completely reasonable, this reasoning. But the literature, as I said, is raising a concern, like, what if an event that we gave up to get protected against it occurs? What if? So we say, and this is, as I said, fully motivated, I get protected only with respect to the event with the highest risk, and the other ones I give up. But what if they occur? So what if something which is not really expected occurs. I recently authored a paper in Italian, by the way, which is titled The Impossible Flood. And the paper points out that indeed, in the presence of climate change, something that we don't expect may occur. So what if the flood occurs? So basically, the literature is saying, okay, you make a decision, you get protected against a risk that is the highest one, but don't forget to make an assessment of what if the impossible event occurs. So what if a flood with a return period of, say, 10,000 years occurs? By the way, usually we have norms that suggest the amount of the return period for the design of adaptation actions. So if we design a dam in Italy, there is the law in force suggesting the return period for the design, which is varying between 500 and 1,000 years. So it means that I designed the dam with respect to an earthquake that has a return period of 1,000 years. I designed the safety discharges for the dam on the basis of a flood with a return period of 500 years. The law in force, when talking about design of infrastructures and structures, tells you the return period for the design. This is why I really wanted to learn this definition, because very often the law in force tells you that the European Flood Directive suggests the return period for the design of the levees, which is about 200 years, levees of the big rivers. Now, what if an event of a return period of 10,000 years occurs, which is possible? By the way, the flood in the Marche region in Italy, it has a return period that has been estimated in 500 years. And other flood events that recently occurred in Italy have a similar return period estimated, which means that, they happen. And in the presence of climate change, they may become more likely. So this is what the literature is suggesting. Okay, this is fine. Risk-based estimation design is fine. On the other hand, don't forget to evaluate what if. What if? And we will make a further reasoning later on, but I don't want to make it now. And but I want to anticipate the concept. The concept is that this exposure curve should be extended on the right and see whether it has an asymptotical tendency or if there is a sharp increase of exposure at a certain point. If you don't make the assessment, the what-if assessment, you cannot know that. And the literature is also suggesting don't limit your consideration to the economic value, but also look at the risk for people, because it may happen with the risk for people that you get a sharp increase of the exposure of people in the very extreme right of this. And therefore, even if it's an event that has a record period of 10,000 years but kills 1,000 people, this has to be considered. Okay? Particularly in light of recent evidence suggested by climate change. Okay, I think we can, let me just check whether we should conclude here or not. Yeah. Let me just make a rapid check. Probably I'm sure that I said everything and maybe even too much. And for exposure, okay. Okay, no, I think we can consider this topic concluded. Do you have any question? Remote students, any question? Okay, we are a little bit ahead of time, but I prefer to close here, and we will see each other on Thursday virtually. And as I said, I will publish the exam dates today or tomorrow at the latest, and with subscription from beginning of May. If you have any question, keep take a note and ask it on Thursday if you have any additional question that doesn't come to your mind now. Okay, thank you very much.